Hi, everyone. We're looking at our next part of quadrilaterals. And this is how do we classify them or prove what kind of quadrilateral we have based on the different properties that we can say are true. So there's a couple of formulas we need to review first before we can jump into how do we use them for the quadrilaterals. So let's take a look and see what we've got to work with. So the first formula I want to review is the formula for slope. And again, there's two ways that you can do slope, one being rise over run, and then the other being the slope formula, y2 minus y1 over x2 minus x1. So again, what we want to remember for slope is that the slopes help us to tell if they are parallel. So that's going to help us find those opposite sides are parallel because they need to be the same. Or it can help us to tell if they're perpendicular. So again, for the rectangle, the rectangle said that you had four 90-degree angles, and we use perpendicular slopes to tell if that is the case. So for perpendicular, we needed opposite reciprocal slopes. So opposite meaning a sign change. Reciprocal means, again, flip the fraction over. All right. Now, one of our other formulas that we want to review for a little bit is the distance formula. And we've seen two versions of distance, or how did we find the length? One is your slope distance formula that we have there, the square root of x2 minus x1 squared plus y2 minus y1 squared. The other way we looked at distance was with the Pythagorean theorem, which the c was our side of the figure. And we can use the a square root of a squared plus b squared. And that's probably the one that I'll use for these examples, just because it's a little bit faster. Now, with our quadrilaterals, we also had properties that dealt with bisecting, or the diagonals, especially, were the ones that cut each other in half. So to find where that halfway mark is, or find where the middle is for bisecting, we have the midpoint formula, which said add up the x's of the ends, divide by 2, add up the y's, and divide by 2. And so again, this is what we use to prove that they are being bisected. We use that with our diagonals, because again, if they're bisecting each other, the midpoint should be the same. So let's see how we use this with a figure. So example 1, we have these 4 points for M, I, N, and A, and we want to say if it's a square, if this figure is supposed to be a square, then the following properties are going to be true. So we're going to prove that this shape is a square. Now, since it's got all of the properties of our figures there, we have to prove every property. So we'll start with the parallelogram and prove that one. So the first thing that the parallelogram said, oops, sorry, let me erase that dot. All right, for parallelogram, we have to prove, first off, opposite sides are parallel. So opposite sides parallel. And that's where the slope comes in. So we're going to start with the slope formula for our opposite sides. And to save some time, I'm going to use rise over run. So let's get these points graphed and see what happens. All right, so we have point M, and I'm going to zoom in here just a little bit. Point M is sitting at 0, 5. Oops, let me move this down. Excuse me. All right, so there is our M. Then we have I is at 4, -1. N at -2, -5. So let me move this up. So -2, 1, 2, 3, 4, 5. There's N. And then A is at -6 and 1. And let's connect these and see what's going on. All right, so let's see what we have. I'm going to zoom out here so we can get a better view. So it does kind of look like a square based off of the drawing we have here. But again, we don't know for sure until we prove it. Oops, sorry about that. My eye is a little too far out. Sorry, 1, 2, 3, 4, -1. There we go, sorry. All right, so now for each of these sets of sides, again, opposite sides are supposed to be parallel. And so we're going to prove that by finding the slopes. So I'm going to start with A to M. And again, I'm going to use rise over run to save a little time here. So for A to M, I had to go up 4 units and then to the right 6 units. So let's come over and write that down. So for segment AM, I'm going to put a teeny little m there so that I know I'm finding slope, was a 4/6. And when we simplify or reduce that, I get 2/3. So that's what I want to use. Now let's go with the side opposite of that. Go back over to our picture, which would be N to I. So again, N to I, I'm going to draw it on the outside here. We can go to the right 6 and up 4, but again, up will go on top, right will go on bottom. So again, 4/6. So for segment NI, and again, a little bitty m there just because I'm dealing with slope, another 2/3. So far, so good, they match. They are the same. Now let's do the next pair of opposite sides. Let's start with segment AN. Little m there for slope. Let's go check out that one. All right, so A to N, this time I have to go down. So I went down 6 and to the right 4. Now this time, since I go down, that means it's negative. So a -6/4, which means I have a -3/2. All right, and then the side opposite of that would be MI, straight across. And again, the little m there, let's find that one. All right, so again, so I don't mess up my picture, I'm just gonna do the slope on the outside. So right 4, down 6. So again, because I go down, that means my slope is negative. So a -6/4. Guess what? It's the same for a -3/2. And those two are the same, which means this is in fact a parallelogram for the first part of it. Now, the other properties that go along with parallelogram, opposite sides are congruent. So now let's do that. So for opposite sides congruent, this is where the distance formula is going to come in. We need to find the length of each of these sides. Now, because we've already got our slope rise over run drawn on the picture, I am going to use the Pythagorean theorem in order to find that, because I'm going to use some of the same numbers that we just did for the slope. So let's go back over. Notice each of these pieces of that possible square is now the hypotenuse for each of those triangles. So I'm going to use each side of that square with being my right triangle. So I'm going to start this time with A to M. So segment AM. Whoops, and I don't need the segment symbol up there because no segment means length. So the length of AM is going to be the C. Is the square root of, now I need A squared and B squared. And let's go get that from the picture. All right, so A to M. So there is my A, which is 4. There's my B, which is 6. Let's plug those into the formula. Four squared plus 6 squared. So again, if we need it, this is a 16 and a 36. Add them together, I get the square root of 52. Now, for now, I'm not going to simplify this down because I just want to compare it with the others to see if I get the same square root for everything, then I know my distances. Let's try the next side, working our way around. Now we need the length of M to I. So again, that is my C square root of. Let's go over and count. MI. All right, so there's my A, which is 4. I always let my short side be A. But in reality, guys, just remember, it doesn't matter which is which. You get the same either way. And a B of 6. So same 4, same 6. So the square root of 4 squared plus 6 squared is another square root of 52. So far, so good. But again, these two sides are not across from each other. Let's keep going. So IN for that segment. The square root of, let's go over and get it. All right, so we've got a 4 and a 6. Same two numbers. Same 4 and same 6. So 4 squared plus 6 squared, square root 52. And we'll do our last side in A. Let's go see what we have for our last one. So again, there's a 4, there's a 6, same two numbers. So far it's looking really good. 4 squared plus 6 squared, another square root of 52. So again, opposite sides are all the same. So that proves that it is at least a parallelogram, because again, opposite sides are congruent, even if they are all ending up to be the same. So now let's do our last part, because the last thing that we saw with parallelograms is the diagonals have to bisect each other. So let's get our two diagonals in here first, so I know what segment to actually find the midpoint on. So now we need, oops, sorry, that's way too big for this space. There we go. So we need to know where the diagonals bisect. So let's get those two lines drawn up there so I know what endpoints I need to use. All right, so one of our diagonals connects A to I. So I'm going to need that one. The other diagonal connects M to N. So I need those two spots so that I can see exactly where they cross. Now, again, remember, just because we find the midpoint of each one, it doesn't necessarily mean that the picture might line up with this. Because again, this is a drawn by hand picture. So let's hope that I can actually draw these lines straight enough to end up where they might need to be. So right now it looks like maybe right there is what our midpoint should be. But again, we have to prove it. So let's go down and prove this now with our midpoint formula. All right, so A to I is the first one we did. So for segment AI, those 2 points that we used, A was a -6, 1, and I was 4, -1. Let's put these in our midpoint formula and see what happens. So again, midpoint says add up the two x's. So that is a -6 and a 4. So -6 plus 4, divide by 2. Then we do the y's, 1 plus -1 over 2, which will in turn, we have a -1 and 0 for our final. -6 plus 4 is a -2. -2 over +2, -1. All right, now let's do the other one. M to N, segment MN. So M was 0, 5. N, -2, -5. So let's add up those x's. 0 plus -2 over 2. Add the y's. 5 plus -5 over 2. All right, when I simplify that down, again, I have 0 plus -2 is -2. -2 over +2, -1. And then our y's, -5 plus, 5 plus -5, 0. 0 divided by 2 is a 0. They are the same. So right now we have proven it's a parallelogram. So let's go back up to all our properties. All of that was just for parallelogram. Now we need to check rectangle, and then we'll check rhombus. Now, since a rectangle is a parallelogram, we don't have to go through all that again, and we can use some of the same information with the rectangle. Because rectangle now says we need the lines, the sides to be perpendicular to create those right angles. So let me get these extra dots out of the way. Now we're going to do rectangle. So the two specific things we need for rectangle, because we've proven everything else. First thing is 4 congruent angles. Which means they're all 90 degrees. This is where the slopes come in. I'm not going to do the slopes again, but what we're looking for are those opposite sign changes, and the refractions need to flip over. So if I'm looking at segment AM, its slope, hence the little m there, was a +2/3. AM is right up next to AN. So segment AN had a -3/2. So that is in fact a 90-degree angle there. They're perpendicular. So AM and AN, that was the angle on the far left. So we're going to keep working our way around. Now AN connects to NI. And its slope was the same as AM's because they were parallel. So it had a 2/3. So far, so good. And then our last one, MI, had a -3/2. So they were all opposite reciprocals. They alternated as we went one side to the next. So that was proven. Now the only thing left to prove with parallelogram, with the rectangle, is you need congruent diagonals. So we need to check the length. So we're going to have to find the slope of each of those two diagonals. So A to I is the first one we're going to have to do. And then we'll need to do MN. So let's go back to our pictures and see what we've got. So now we're only using the inside. And again, I'm going to use Pythagorean theorem so that we can find these. All right, so A to I, I'm just going to briefly draw the triangle here. So there's our triangle. We've got 2. and over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So a 2 and a 10. Oh, sorry. Sorry about that. Kind of moved out of position for me. There we go. So then 2 squared plus 10 squared. All right, so 2 squared is a 4, 10 squared was 100. So that gives us the square root of 104. Again, I'm not going to break it down. I don't want to simplify it. I'm just going to leave it as is so that I can compare it to MN. Let's go up and get the other one. Now, while you're doing these, if you need to erase as you go along or draw another picture so that everything doesn't start overlapping each other, there's nothing wrong with that. But for time, I'm using the same picture. So I've got 2 along the bottom. And another 10. So the same 2 and the same 10. So 2 squared plus 10 squared, 104 inside my square root. And again, they are the same. So right now we've proven it's a rectangle. Now, keep in mind, if you have to prove it's a rectangle, you may have to also prove the parallelogram properties, unless it specifically says prove the parallelogram is a rectangle. If it already says parallelogram in the situation, in the story, you do not have to prove all those properties. But if it says prove the rectangle is prove the quadrilateral, then you have to do all the parallelogram stuff as well. All right, last one is the rhombus. Now remember, rhombus has separate properties from the rectangle. Okay, rhombus specifically says you need 4 congruent sides. So we need the distance, which we've already got, because we said that A to M was the square root of 52. We did this with parallelogram. Then we had MI, which was the square root of 52. Then we had IN, and then NA. So all of them were the same. All of them are the same, so that proves rhombus. With the parallelogram, yes, they were all 4 the same, but we only needed to prove that the opposites were congruent. Hence, AM and AN, or AM and NA, same, and MI and IN, the same. The other thing that is specific to a rhombus that the others don't necessarily have is we have to prove that the diagonals are perpendicular. Remember, that's what that upside down T stands for. That is where the slopes are going to come in. So we're going to use that same 2 and that same 10. One of our diagonals, which we've already kind of talked about, was AI. So the slope of A to I. Let's go take a look at it and go back to those triangles we drew to find the distance. All right, so A to I go down 2 and over 10. So 2 and the 10. So down goes negative, right is positive. So that is a negative 1/5. And now the other diagonal, MN, so segment MN. Let's go look at that one. So we went 2 to the right and up 10. So up 10 means 10 is a positive and on top, 2 to the right, positive on bottom, so a positive 5 over 1. They are, in fact, perpendicular. So now we have proven everything to make sure this is a square. So now we can say MINA is a square, because we proved everything that we needed to prove. Now, sometimes we can use these different formulas to prove whether or not what kind of shape you have, what kind of classification can you give it. So let's check out our next two examples. All right, example 2, classify the quadrilateral if. So let's check this one out. I'm going to come over to my graph. So we have A is at -6, +4. So there is A. B is at -2, 8. Let me move this down just a little bit. So there is B. C is at 3, 3. And D is at 1, -3. And we need to prove what this is. So we'll start with parallelogram. And so we need to know first off, what are the parallel sides we might have? So we always start with parallel sides. So we'll check for parallel. So we need the slope of A to B. Let's go count it. All right, so to A to B, we went up 1, 2, 3, 4, over to the right, 1, 2, 3, 4. So 4 over 4. Which means we get a slope of 1. Now, opposite of that is the next one we need, which is CD. So segment CD slope. Let's go count that one. All right, so again, I'm just going to keep this outside of my figure. So 2 across to the right, and 1, 2, 3, 4, 5, 6 up. So 6 over 2. Which gives me a slope of 3. So right away, these are different. And what this tells me, parallelogram is out. So rectangle is out, rhombus is out, square is out. Only thing left to check is kite or trapezoid. Kite had no parallel sides. Trapezoid had one set. We need to know what's going on with those other two sides. So let's check those out now. We need the slope of BC. And then of A to D. Let's go count those. So BC, again, I'm going to stick to outside of this figure. We've got to the right, 1, 2, 3, 4, and then down 1, 2, 3. Oh, I'm sorry, I didn't go over far enough. So 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5. And again, going down means negative. So -5 over 5 is a -1. Let's see the other one. A to D. Down 1, 2, 3, 4, 5, 6, and then to the 7, sorry, down 7, and then now -7. 1, 2, 3, 4, 5, 6, 7. So -7 over 7. For a -1. So these are the same. You have one set of sides that are parallel. So for that, that means that this figure ABCD is a trapezoid, and that's all we can prove. We just wanted to classify it for one of our quadrilaterals, trapezoid. Now, we can also check and see if it is isosceles by doing congruent sides. So let's do that. Because let's see if we can be more specific and check those congruent sides. And again, since I've already got my numbers there from the slope, I'm going to use those for Pythagorean theorem. So what we're checking for are the legs. So the only distances that we need to check, we don't have to check them all. We are checking only the ones that were not parallel, which means we are checking the length of AB. Oops, and I don't need the bar. And I need to check the length of CD. Because again, for an isosceles trapezoid, we only have to check the ones that were parallel. So let's check those out and see what we get. All right, so the first one we need to check, A to B, which is a 4 and a 4. So let's say it doesn't matter which one is A and B because they're exactly the same number. Let's see what the length is. Oops, sorry, too far. So 4 squared plus 4 squared. So that is 16 plus 16. So the square root of 32. And now we're going to check C to D, which is our 2 and 6. So 2 squared plus 6 squared. So this time that's a 4 and a 36, which is the square root of 40. They are not congruent, not isosceles. So all I can do is call it a trapezoid. All right, our last example. Again, another classify given those shapes. So let's see what we have. Let's get our figure up here. All right, we have J, which is at 5, 6. We have K is at 0, -4. All right, Then we had L, which is negative 5, 4. Sorry, negative 5, negative 4. And M at negative 5, 1. All right, so there's our figure. So again, we're going to test parallel sides first to see if this is some kind of parallelogram. So let's get the slope. So we need JK slope. I'm just going to go ahead and write them out here. Actually, no, let's go ahead and graph it. All right, so J to K, we went over 1, 2, 3, 4, 5, and then up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So again, because we went up, that goes number, that number is on top. Where is it? There it is. So we have 10 over 2. I'm sorry, 10 over 5, which will give us a slope of 2. So let's keep working our way around the shape here, KL. So the slope of KL and then I'm going to, like I said, I'm going to go ahead and rewrite the rest of these. LM, slope, which we'll find in a second, and then MJ. Let's go find all the ones we need. So KL, there it is. So KL is just 5 across. It's horizontal, it's flat. Those always have a slope of 0. All right, so horizontal flat lines, slope of 0. All right, now we've got LM. LM was vertical, so it's got a rise, but it doesn't have a run. So anything over 0, because again, 0 means there's no run, in this case is undefined. All right, and then our last one, MJ. We've got 1, 2, 3, 4, 5 up, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the right. So 5 over 10. Five over 10, 5 up, 10 right, 1/2. All right, none of these are the same, so parallelogram and trapezoid are out. So the other things that we want to check off are the congruent sides. It's possibly a kite. But again, none of these are parallel. None of these are parallel. All the parallelograms are out and trapezoid is out. Our last option, the kite. And for kite, now we need congruent sides. We want to make sure that there's 2 pairs of consecutive congruent sides, not across from each other. All right, so we need JM and JK to be congruent. So we need their lengths. Both of them had 2, I'm sorry, both of them had 5 and 10. But let's see what we have. All right, JM. Again, it doesn't matter which is which, but let's say the littler one can be A and the bigger one can be B. Same thing for JK. Little one can be A, bigger one can be B. So the length of JM and the length of MJ or JK, sorry. I'm sorry, no bar on top because we're looking for length. But they both are going to have that square root. And again, the A's were the 5s and the 10s were the B's. That is a 25 and 100. So the square root of 125. And same thing for the other, 5 squared and 10 squared. For another square root 125. So those two are congruent, meaning that J is a vertex. And now we need to do the other two sides. KL and ML. Let's go check those out. All right, we have ML and KL are nice enough and easy enough just to count. We don't need to make a right triangle for these because we've got 5 units and 5 units. So again, just count them if they're horizontal or vertical. But they are in fact the same. So that means right now, this is a kite. Because your definition of kite says that you have 2 pairs of consecutive congruent sides. So this is a kite. All right, guys, I hope you enjoyed learning a little bit about how we prove our different kinds of quadrilaterals. Please don't hesitate to reach out to me if you have any questions. Definitely hang out in the Zoom and I can show you some ways that we can use Desmos to help plot these points. But guys, again, if you have questions, definitely let me know. We can work through it. Bye, guys.